Good morning, all. Thank you so much for joining for this. Let us better understand variable frequency drives or VFD. Soft starter is a device which is used only for starting the motor smoothly and that do not have any role after the motor has started. Variable frequency drive is not really meant for a smooth starting. It helps. It's an additional benefit which comes out from the variable frequency drive. It can be used to start the motor by means of reducing the starting current and all, but its main purpose starts after the motor has started, and the variable frequency drive will be there in operation throughout the motor is running, and it is controlling the speed or controlling the frequency or whatever you call it, is controlling something with some objective. There are two key important aspects of variable frequency drive. That's the reason why we are going for a variable frequency drive. Variable frequency drive is used like with only two important aspects. Like that's the two key purposes of variable frequency drive. That's why we are going for a variable frequency drive. What are the two key driving factors why we go for variable frequency drive? One is a process requirements to control the speed or adjust the speed or vary the speed, whatever it is. The second objective comes with an energy efficiency. Even if there is no process requirement, but if there is a place where the variable frequency drive is fitting, if it is able to save some energy, and we know what is the cost of electricity now, and we are talking about also the global warming effects, right? How the electricity is generated. So if you're able to save the energy, then that's an amazing benefit which you can look at from the like variable frequency drive. So you have like two aspects of it. One is the process requirements and other one is like energy efficiency. Let's talk a little more on the energy efficiency. And for that, like let's compare maybe a direct online motor with maybe variable frequency drive motor in the like kind of simulation environment itself. Then we will compare like whether direct online motor is efficient or variable frequency drive is efficient from the energy efficient perspective. Let's take an industry, assume that that industry receives the power supply from the utility at 110 kV. I'm not really going to complicate the things. Let's just quickly take very, very small, simple, fine examples just to compare direct online motor with variable frequency drive. Let's take 110/11 kV, maybe 25 MVA transformer. Just give me a second. I got to move some cursors here and there. All right. So all unnecessary. Like what I have looked at, like 110/11 kV, 25 MVA transformer, and let's compare. Like I'm not really going to model the cables and stuffs. I'm just going to model a motor, direct online motor versus a variable frequency drive, and let's like keep comparing that with multiple other options. And why I am putting all these things, you will come to know quickly. Let's put maybe 5 megawatt. That is 5000 kilowatt motor with a power factor of 0.9315 and efficiency of 0.9457. That's a by default parameter what ETAP gives. Like I'm not really going to change it. So it is 11 kV, 5000 kilowatt motor, direct online start. And of course, we are not really starting the motor. We are trying to compare the efficiency during normal running conditions. I have told like variable frequency drive is used for energy efficiency purpose. Now we are here 5000 kilowatt, that's pretty much done. And probably if we give this variable frequency drive parameters, then we can very much probably, so give the parameters here also. So let's copy this little later. So 5000 kilowatt motor, that's all right. Now I have variable frequency drive which I need to connect with this 5000 kilowatt motor or a 5 megawatt motor. This is precisely explained in this video. I guess like for the benefit, you need to ensure that like you're bookmarking this video and watch it. It's probably a bit lengthy video. I'm not really going to repeat the same thing here. But one thing which I can say, like I have explained exactly like how to model this variable frequency drive. I'm skipping that portion now and I'm moving little quickly. But of course, one important aspect is like the variable frequency drive has to deliver the output power more than what is the input requirements of the motor. When we say 5000 kilowatt, 5000 kilowatt is the mechanical output of the motor, which means the electrical input like will be 5287 kilowatt, including the cable losses. Like variable frequency drive I have directly connected here at motor terminal, but there will be definitely a cable which connects the variable frequency drive to the motor, and including that cable loss, this output of the variable frequency drive should be capable to meet motor maximum power plus cable loss. And it brings to another important question: what should be the kVA rating of the variable frequency drive or that particular motor? I guess like this is in detail addressed in that video, so I am not really going to elaborate that now. But one thing which I can probably say, you need to select the kVA rating of the motor or power factor of the motor in such a way that the output of the variable frequency drive is able to meet the reactive power requirements of the motor. Let me repeat the sentence once very quickly. kVA rating or power factor of the variable frequency drive, when I say this is output of the variable frequency drive, has to be selected in such a way that meets the maximum reactive power requirements of the motor. Right? Please go and watch that video, like how probably elaborated a bit more that video. And coming to this point, like that is output. What about the input? Efficiency of the variable frequency drive will not be 100. That will be in the range of about 92 to 97, 98%. But input power factor of the variable frequency drive could be 100%. Which means variable frequency drive has the capability to generate the reactive power requirement of the motor on its own without drawing the reactive power from the input. And I am probably trying to copy paste the same thing here and trying to connect it. And I am trying to copy the same thing just for the comparison of direct drive versus 6 pulse drive versus 12 pulse drive. That's precisely what I'm trying to do. And I'm done. Like now this gives a beautiful comparison of right. Of course, like for really an important reason, like I'm bringing it the winding configuration also, like you need to be a bit careful when you're choosing the transformer. Like this winding connection has to be like different. There should be 30-degree shift between the LV windings. So one is selected as delta and other one is selected as a star. And HV could be selected as delta or star ungrounded. It should not be star solidly grounded. Right, like I'm just trying to zip that. Anyway, all right, no worries. Let's run load flow analysis now. Let's run load flow analysis now. All right. We got some results. 5,000 kilowatt motor, that's the mechanical output. The motor is drawing 5,287 kilowatt. That's an electrical input. The motor is drawing 2065 kVA or motor is drawing 2065 kVA. That's a reactive power. Power factor of the motor is like what's the input which we have given. Same thing probably repeated here in this portion, but like if you look at the difference, the power consumed, real power consumed by this variable frequency drive is like 5,451 kilowatt. The variable frequency drive which we have installed to minimize the power consumption or to increase the energy efficiency has resulted in higher losses, and probably means instead of drawing 5,287 kilowatt, we are drawing 5,451 kilowatt. But beauty, the reactive power requirements becomes zero. That's because the variable frequency drives, not all the variable frequency drives, but at least the latest variable frequency drives are capable of maintaining input power factor as unity. Coming to the third one, it is a 6-pulse variable frequency drive. It is not direct drive, which needs essentially a transformer. So the difference between this and this, like this variable frequency drive essentially needs a 2-winding transformer. So there is a 2-winding transformer which is connected, which further increase the losses on the transformer, and whatever the reactive power losses in the transformer is also probably reflected on the side. So if you look at 5287 becomes 5451 and that becomes 5588, right? So the losses has drastically increased, and probably because of the advantage of variable frequency drive, it's not really drawing any reactive power, but like here there is a reactive power loss in the transformer that's reflected here. When it comes to the 3-winding transformer, like the losses are slightly different from 2-winding transformer and 3-winding transformer. That's because like what's the impedance, what's the losses, etc. Probably this T2 and T3, like 6-pulse variable frequency drive versus 12-pulse variable frequency drive, which we need to talk about morely from the harmonic analysis perspective, not really from the like load flow perspective. Now the objective of going for a variable frequency drive is shattered. Shall we have the transformer rating less than the motor rating variable frequency drive? Essentially no. So the transformer rating selected should be at least above the power. That's the reason why the transformer is overloaded. All right, like we will correct that. 6 MVA, 3 MVA, 3 MVA. All right, let's run load flow. Yeah. So now let's looking at the results. So still, if you look at the purpose of going for a variable frequency drive, is to enhance the energy efficiency, minimize the power consumption. But if we are looking at now, like going for a variable frequency drive has increased the power consumption. Going for the variable frequency drive with the transformer further increases the losses. Of course, though there is the reduction in the reactive power consumption, technologies available in the variable frequency drive, which they are able to keep the input power factor as close to 1 or 0.99. Please refer the data sheet of the latest variable frequency drives. Their inherent capability, like they are able to prevent the reactive power consumption from the grid, which maintains the power factor. Right. Now, like, what's the purpose of going for a variable frequency drive? Do not have any meaning if the motor is running at 100% load always. There is no point in probably going for the variable frequency drive. When the load is not constant, the load is keep fluctuating, then normal induction motor which do not have any control over a speed, the power consumption of the motor could be optimized if we are going for a variable frequency drive where we adjust the voltage and frequency so that only the required amount of power is consumed by the motor, the excess power can be saved, and that's where the energy efficiency brings in. So we need to be very careful where we have to select variable frequency drive and where not. If there is a process requirement for a speed control, there is no other go, we have to go for a variable frequency drive. But if there is no process requirements, still variable frequency drive can be selected where like the loading on the motor is not constant. By means of going for a variable frequency drive will help you to optimize the energy consumption or minimize the energy consumption. See the screen, like when your motor is decided or it's running predominantly more than 90% of the load at all the times, then going for this variable frequency drive is meaningless. But assume that sometimes if the load needs only less power or the power consumption or the demand of the load is keep changing, then there is always an advantage of going for the variable frequency drive. Instead of going for a soft starter, you can go, but it is expensive. So only if your starting is the only requirement, and after the starting, like the motor runs at a constant speed, go for a soft starter, not for a variable frequency drive. If you're going for a variable frequency drive, like you can go for some applications like this. You can see here what happens if I'm reducing the frequency from 100% to 95%. You can look at like what's the connected load in percentage. If I'm just reducing the frequency from 50 Hertz to 45 Hertz, I have just reduced the frequency from 50 Hertz to 45 Hertz. You can see what's the change in the power consumption. So is it making a sense? Definitely it's making a sense on the power consumption, but this is truly applicable where the load is not constant and the load is intermediate and it is keep changing with respect to frequency. Why do we use the transformers? Some variable frequency drives like 6 pulse direct drive do not need a variable like a transformer, but normal 2-winding transformers might be needed for a 6 pulse variable frequency drive to handle the harmonics or to handle the unbalance or for the isolation purpose or for EMC requirements. It depends upon how the variable frequency drive is manufactured. You can Google it with a direct drive or like a 6 pulse 12 pulse drive, you can understand. And of course, if you're going for a 12 pulse variable frequency drive, there is no other go. You have to definitely go for a 3-winding transformer. I guess like that gives like some base idea of like how to select the transformers or whatever it is. Once the motor has reached its rated speed, if you're bypassing the variable frequency drive, please don't go for a variable frequency drive, just buy a soft starter. Means the purpose of the variable frequency drive starts when the motor has reached its rated speed, and then probably for the process requirements to control the speed or for energy efficiency. If you have bypassed the variable frequency drive after the motor has started, then that serves only as a purpose of a soft starter. But variable frequency drive is much beyond the soft starter. Variable frequency drive, as we discussed, it can control the speed, it can control the frequency, it can control the power consumption, it enhances the energy efficiency, it reduces the reactive power consumption from the grid, improves the power factor, reduce the reactive power requirements and whatnot. Like it has like quite a lot of purpose. But if you have decided to bypass the variable frequency drive in running, then it's better to go for a soft starter, not for a variable frequency drive. Like if you use any soft starters, like when you are controlling the voltage, torque is proportional to square of the voltage. So whenever you are controlling the voltage, obviously the torque will change. Torque is proportional to square of the voltage. You will lose the torque if you're using a soft starter, any soft starter. Soft starter injects the harmonics in the system only during starting, only for a few seconds, not definitely few minutes, maybe 10, 20, maximum 30 seconds. But like your variable frequency drive is going to stay there along the motor is running. That means across the time, and it's keep going to inject the harmonics